Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on theory of numbers, lecture number 35, in which I will give the concept of Fermat's little theorem. Before giving the concept of Fermat's little theorem, I would like to give you some basic ideas which will inspire for the Fermat's little theorem. Let P be a prime number and let P equal to 5. A be another integer such that P does not divide A. Here we take A equal to 3. Therefore, 5 does not divide 3. Since 5 minus 1 equal to 4, therefore we get positive integers less than 5 as 1, 2, 3, 4. Now, A equal to 3, we take 1 multiply 3. 1 multiply 3 is congruent to 3 modulo 5, because 1 multiply 3 is 3. 3 minus 3 equal to 0, which is divisible by 5. Let this is number 1. Now we take 2. 2 multiply A. A means 3 is congruent to, this is 6. 2 multiplied by 3 is 6. If we divide 6 by 5, we get remainder 1. So here we write 1 modulo 5. This is number 2. Now we take 3. 3 multiplied by 3 equal to 9. If we divide 9 by 5, we get remainder 4. So here we write 4 modulo 5. Let this is number 3. Now we take 4. 4 multiply 3. 3 is A. Congruent to 4 multiplied by 3 is 12. If we divide 12 by 5, we get remainder 2. So we write here 2 modulo 5. This is number 4. If we multiply 1, 2, 3, 4, we get 1 multiply by 3 left side, multiply 2 multiply 3, multiply 3 multiply 3, multiply 4 multiply 3. congruent to here 3 multiply 1 multiply 4 multiply 2, that is 3 multiply 1 multiply 4 multiply 2 modulo 5 implies that here 1 multiply 2 multiply 3 multiply 4 multiply 3 to the power 4 is congruent to 1 multiply 2 multiply 3 multiply 4 modulo 5. Since GCD of 1 multiply by 2 multiply by 3 multiply by 4 and 5 is 1. Therefore, we may cancel this both sides. Implies that 3 to the power 4 is congruent to 1 modulo 5. Since GCD of 1 multiply by 2 multiply 3 multiply 4 and 5 equal to 1 implies that 3 to the power 5 minus 1 is congruent to 1 modulo 5. If we put 3 equal to A and 5 equal to P, then 5 will be written as A to the power P minus 1 is congruent to 1 modulo P. And this formula is the Fermat's little theorem. Now, I will give the concept of Fermat's little theorem. Now, we state Fermat's little theorem statement. Let P be a prime number and A be a positive integer with P does not divide A, then A to the power P minus 1 is congruent to 1 modulo P. Now we prove this. Let us consider P be a prime number and A be a positive integer such that P does not divide A. This is number 1. Since P is a prime number and P does not divide A, therefore from 1 GCD of P and A is 1. This is number 2. Now let us take P minus 1 numbers of integers as follow. 1 multiply A, comma 2 multiply A, comma 3 multiply A, comma, dot, dot, P minus 2 multiply A, P minus 1 multiply A. Firstly, we shall show that number 1, none of these integers are divisible by P. Number 2, no two integers are congruent modulo P. That means if we divide any two integers by P, we may not get the same remainder. Firstly, we prove these two. Number 1. Let K is greater than equal to 1, less than equal to P minus 1. Therefore, P does not divide K. This is number 4. Now let A be a positive integer such that P does not divide A. This is number 5. If possible, let P divides AK. This is number 6. Using 5, we get in 5 P does not divide A, therefore P divides K, which is against 4. Therefore, our assumption in 6 is wrong. Therefore, P does not divide AK. This is number 7. Number 2. Let K and M are two integers such that K is greater than equal to 1 less than equal to P minus 1 and M is greater than equal to 1 less than equal to P minus 1. Let this is number 8. Let K is not equal to M and if possible K A is congruent to M A modulo P. Let this is number 9. Since GCD of A and P equal to 1, therefore from 9 K is congruent to M modulo P. This is number 10. Since K is not equal to M and K is greater than equal to 1 less than equal to P minus 1, M is greater than equal to 1 less than equal to P minus 1, therefore if we divide K by P, we get remainder K. Similarly, if we divide M by P, we get remainder M. So, we do not get same remainder when K and M be divided by P. Therefore, 10 is not possible. Therefore, our assumption in 9 is wrong. Hence, Ka is not congruent to Ma modulo P. Therefore, no two integers 1a, 2a, dot 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 p minus 1a are congruent modulo p. Therefore, if we divide these integers by p, we get different remainder. These remainders are one, two, three, dot 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 p minus 1. Now let us arrange the integers of 3. Integers of 3 be 1 multiply a, 2 multiply a, dot 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 p minus 1 multiply a, such that least positive residue modulo p of these integers be 1, 2, dot 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 p minus 1 respectively. By taking product of these integer congruent modulo p, we get 1 multiply a, 2 multiply a, multiply p minus 1 multiply a congruent to, here remainders, 1 multiply 2 multiply dot 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 multiply p minus 1 modulo p. Let this is number 11. Implies that 1 multiply 2 multiply 3 multiply dot 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 multiply p minus 1 a to the power p minus 1, a multiply by a, p minus 1 times. Congruent 1 multiply 2 multiply 3 multiply p minus 1 modulo p. Since 1 multiply 2 multiply by 3 multiply by p minus 1 is relatively prime to p. That means GCD of p and this product be 1. Therefore, we may remove this product from both sides. This implies a to the power p minus 1 is congruent to 1 modulo p. Hence, Fermat's little theorem is proved. Now we prove a theorem. Theorem is, if p is a prime number and a is a positive integer, then a to the power p is congruent to a modulo p. We prove this theorem in two cases. Case 1. Let p does not divide a. Then by Fermat's little theorem, a to the power p minus 1 is congruent to 1 modulo p. Let this is number 1. Since a is congruent to a modulo p, because a minus a is 0, which is divisible by p. This is number 2. multiplying 1 and 2, we get a to the power p minus 1 multiply a is congruent to 1 multiply a modulo p, implies that a to the power p is congruent to a modulo p. Therefore, case 1 is proved. Now case 2. Let p divides a, implies that p divides a to the power p. This is number 4. From 3 and 4 we get p divides a to the power p minus a, implies that a to the power p is congruent to a modulo p. Proved. Now we solve a problem. Problem is using Fermat's little theorem, find the least positive residue of 2 to the power lakh modulo 17. Let p equal to 17, which is a prime number, and let a equal to 2. Therefore, p does not divide a. Therefore, by Fermat's little theorem, a to the power p minus 1 is congruent to 1 modulo p, implies that 2 to the power 17 minus 1 is congruent to 1 modulo 17, implies that 2 to the power 16 is congruent to 1 modulo 17. Raising power both sides, 2 to the power 16 to the power 6250 is congruent to 1 to the power 6250 modulo 17, implies that 2 to the power lakh is congruent to 1 modulo 17. Therefore, our residue is 1. Now we solve the next problem. Problem is m and n are primes, then show that m to the power n minus 1 plus n to the power m minus 1 minus 1 is a multiple of m multiply n. Now we solve this. Let m and n are two distinct prime number. Therefore, m does not divide n and n does not divide m. If we consider m does not divide n and m is a prime number, then by Fermat's little theorem, n to the power m minus 1 is congruent to 1 modulo m. implies that m divides n to the power m minus 1 minus 1. This is number 1. Since m divides m to the power n minus 1, this is number 2. From 1 and 2, we get m divides m to the power n minus 1 plus n to the power m minus 1 minus 1. This is number 3. Implies that m to the power n minus 1 plus n to the power m minus 1 minus 1 is congruent to 0 modulo m. This is number 4. Similarly, we may show that m to the power n minus 1 plus n to the power m minus 1 minus 1 is congruent to 0 modulo n. This is number 5. From 4 and 5, we get m to the power n minus 1 plus n to the power m minus 1 minus 1 is congruent to 0 modulo LCM of m and n. Implies that m to the power n minus 1 plus n to the power m minus 1 minus 1 is congruent to 0 modulo, since m and n are prime numbers, therefore their LCM will be m multiply n, mn. Therefore remainder equal to 0. Hence m to the power n minus 1 plus n to the power m minus 1 minus 1 is a multiple of m multiply n. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.